So like we were talking about, in theory, you could get exact area if you had infinite rectangles, trapezoids, or paraboloids. So exact area is a hypothetical or a theoretical. So theoretically, the RAM, the trap, and simp methods would be perfectly accurate if we had infinite intervals or subdivisions. But that's a theoretical, it's hypothetical. You can't, it's not possible. Even the computers, even our calculators can't do infinitely. They just keep cycling and keep cycling and keep cycling. So we need something else. You'll see this sometimes. You'll see this symbol. Okay, that's the Greek letter sigma. It means the addition of, and when we write rectangles, we write base times height. So the addition of base times height, add them all up, assuming in front of that the limit of the number of rectangles you have approaches infinity. So it's the limit of the summation of every possible combination of base times height. In calculus, we write the base as dx, and we write the height as f of x. Okay, the base is the differential along the x-axis, so it's that small, tiny little bottom, and then the height, f of x. So what Leibniz came up with, this was all Leibniz, is he came up with the integral symbol. And so Leibniz's way of doing area was to use the elongated S. And that elongated S means the limit of the summation as you approach infinitely many subdivisions. That's all contained in that one elegant symbol. He's like, I'm sick of writing sigma all the time. I'm sick of writing limit all the time. I'm sick of writing. And so he came up with, he devised this symbol. And then for elegance sake, he switched the order so that we had f of x coming on first and then dx coming later. And then he also had the idea of adding the bounds, where a would be the first part of your interval and b would be the end. So that is called the integral symbol. We credit it to Leibniz. It means infinitely many subdivisions beneath the boundary of an area, but above the x-axis. All right, so as long as you understand what that means, then you can do a lot of these problems. And you don't need a ton of calculus to be able to do it. You just need a good working knowledge of geometry. So you might have find the integral from 0 to 2 of the function that is the square root of 4 minus x squared times the differential and above the x-axis. So that problem looks intimidating until you think of it geometrically. This is just a geometry question. If you understand that the meaning is find the exact area between the numbers 0 and 2 of the shape of a quarter circle, you don't need anything else other than the knowledge of a little geometry. So the square root of 4 minus x squared is a semicircle of radius 2. It's the upper half. And so we have a nice semicircle, perfect radius of 2. And my limits are limiting me to the boundaries from 0 to 2, so I'm only limited to this first quadrant. And so if you can think of this in geometric terms, then all you got to do is know some geometry. You know that the answer to finding the value of that integral is going to be 1/4 of pi r squared. And so in this case, it would be 1/4 of pi times the radius of 2 squared, so the answer is simply pi. Think about it geometrically. Okay, next question. All right, finding the integral. This time, that starts at a value of -2 and ends at 5. The function is 7x, and it's related to the x-axis. That dx always means that the base of this is considered to be the x-axis. Again, we want to think of this geometrically. So 7x is a very steep linear line. So we'll sketch 7x as a linear line. We're going from a value of -2 to a value of 5. On the negative side, the shape is a triangle whose boundaries are below the x-axis. And on the side 0 to 5, its boundaries are also a triangle, but it's above the x-axis. And so if we think of this geometrically, we're just considering 2 triangular shapes. And so this is going to be 1/2 the first base times the first height plus 1/2 of the second base times the second height. So 2 triangles added up to 1. So my first triangle is 1/2, the base value is 2, and what is the height of that triangle beneath the x-axis following the function of 7x? -14. The second triangle, its base is 5, and its height following that function is a height of 35. So this is -14 plus 175 over 2. And so we have a negative triangle added up to a positive triangle, which gives me a net total answer, an area of 161 over 2. A net area. So your shapes are going to be triangles, trapezoids, rectangles, circles, semicircles. Okay, let's consider this shape. All right, given the shape of the sine function. So we all know what the wave of sine functions are. That shape of the sine function going from 0 to pi has a given value of 2. And so then we need to find the value of 0 plus pi of the function cosine x plus 1. And again, we want to think of this geometrically. So consider what you're given. You are given the shape of sine, which we know looks like this, from 0 to pi. Oh, I'm sorry, yes, dx, thank you. There should be for both of them. Let me get that so that we're correct. Our notation is correct. Thank you. Dx equals 2. Okay. All right, so we know that any area shaped like this with one arch of the sine graph, we're given that that is the value of 2. So let's think about geometrically what the other shape looks like. So cosine, we know that cosine looks like this from 0 to pi, going from 1 to -1. We also know now that we are bumping this up by the value of 1. And so that shape, added 1 to it, is going to look a little differently. I didn't leave myself enough room here. Let's see. Do this so I can leave myself a goodly amount of room. All right, let's do this. Here is cosine. Now let's move it up 1. So moving it up 1 on my y-axis means I'm going to look like this. So my job is now to figure out what the shape of that all is, what the value of that all is. And so again, we want to approach this geometrically. I'm going to erase the original one so that I can subdivide this up a little bit. Okay. So in here, I'm going to go from pi halves. I see 3 different shapes. Right? I see this rectangular shape. I see a part of a cosine curve, and then I see a different value right in here. So I'm going to need to find the areas of all of those thinking geometrically. Okay, well, let's look at the green shape. Compared to the original graph, where have I seen the green shape before? Half of it, right? Like if I took my sine graph and I did half of it, those 2 shapes are exactly the same. And so since we know that sine has a total value of 2, then half of it must have a geometric value of 1. So we know that that is 1. All right, let's think about the rectangle, the yellow shape. Okay, what is the area of that simple rectangle? Base times height, right? So the area of that is pi over 2. Okay, now how about the pink, pinkish purple? What is that going to be? Close. Let's see. Yes, very good, boy. You got it. All right, how did you think of that?
The blank space is the green space.
Okay, so he thought of it this way. This blank empty space right above it is the same shape as the green space on the other side. Those are equal. So these 2 spaces are the same. So this new green space with the pinkish space together make a rectangle. And so that rectangle is pi over 2, but then you have to subtract out the green space, so the pink space must be, say it again.
Pi over 2 minus 1.
Very good. So to put all of that together, the value of this cosine is going to be 1 for the green space, pi halves for the yellow space, and then pi halves minus 1 for the pink space. You add all that together, and what do we get? You get pi. All right, 2 pi over 2 is pi. All right, then you get pi. All of that from the value of this sine being 2. So you're just thinking of it in geometric puzzle pieces. Okay, any questions about the 3 geometry questions we've done so far?
For the, you did like the triangle one, like
Yeah.
for the base, you just did like positive 2, so you just like, is it just like distance, just like?
It is distance. Okay. Yeah, thank you for asking that. All right, so this is going from -2 to 0, right? And then we go from 0 to 5, right? So the base, the dx, is always the bigger one minus the smaller one. And then for the other one, the base was 0 minus -2. And so that's also 2, yeah. You always do the one farthest to the right minus that one, so yeah, it's distance. Okay, last one. Okay, find the area starting at 0, ending at the number 5 of the function e to the negative x squared above the x-axis. Okay, e to negative x squared above the x-axis. Now, we knew what a semicircle looked like. We knew what a triangle looked like. We even knew what sine and cosine looked like. But do you know what e to the negative x squared looks like? All right, so this would be in a section where you could use your calculator. So let's look at a picture of this. Okay, so grab out your calculator and go ahead and graph that on that window from 0 to 5. I have a general idea what this looks like. I know it's always going to be positive because exponentials are always positive. Okay, does anybody have the shape of that? It's a tiny little, you got to really zoom in on it. If this is the number 1, it sort of kind of comes down like that, up to 5. Okay, this is not a known shape to us. It doesn't have, does not have the properties that sine and cosine do. It's not a semicircle. It's got decreasing value of area as we go up to here. So this is not something that we can do with geometric shapes like rectangles and triangles and trapezoids and semicircles and stuff. So your friend and mine, Math 9. So from our Math 9, that integration feature, we get an estimate of this area to be 0.886. So if you are allowed to, if you're not grayed out from using your calculator, by all means, use FNIT, for sure. No sense in trying to do lots of it by hand. But when you're blocked out, then that's when you want to use the geometric shapes.